Okay, so my own approach to finding young stars. Many famous clusters have already been observed with Spitzer, and thus either Gutermuth did this kind of analysis himself, or his collaborators did it with him, or somebody was doing that kind of analysis on it. But if you don't already have four bands of IRAC for a given patch of sky, you can't use his method. Things that don't have four bands of IRAC at least have WISE, because WISE did the whole sky. But WISE isn't as sensitive as Spitzer, and it doesn't have as high spatial resolution. So, you do what you can with what you got. 2MASS can provide JHK over the whole sky, but deeper observations in 2MASS are super helpful. And UKIDS and VVV both provide that kind of data, but only in certain regions. There are lots of relatively recent released optical data, including Pan-STARRS, Gaia, and IFAS. Pan-STARRS and IFAS are not all sky. IFAS is just the galactic plane, and Pan-STARRS is just pretty much the northern hemisphere. But if you can get them, they are super helpful. The other infrared datasets that you could use include Akari, Herschel, and NEOWISE. NEOWISE is just the shortest two bands from WISE, but it also has time variability. And the reason that's important is that variability is also a good way of finding young stars. You can do variability in the infrared from NEOWISE, but you can also do variability in the optical from two different surveys called ZTF or Assassin to help assess whether or not the stars are really young. My own approach is I tend to want to fold in all the information we have from all of these other places to decide whether or not I still believe any given star is young. I've done many different things to find young stars over my career. I've used UV-XS. I've used tons of infrared XS searches, both the Koenig and Gutermuth approaches, plus my own homebrew version. I've used X-rays. We don't often have it for NITAR projects. I've used variability. We've got some access to some of that for infrared. We might have optical depending on what NITAR teams are doing in what region. There's emission. I've used emission lines. I've done this mostly using H-alpha, some calcium emission, but depending on what target we pick for NITAR teams, we might have some H-alpha available through IFAS. Spatial location is pretty important. Distance and space motion, if you have it. If we've got Gaia data for our targets, then we can use distance and space motion. But Gaia doesn't always work for the targets that we pick, because Gaia is, at least for the current data release, is only going to give us reliable distances out, I think, to about 3 kiloparsecs. If we've got something further, then it's not going to help too much. If I find that finding young stars works best if you can include everything that you can. So use IRAC and 2MASS, but then get the optical, make SEDs, make as many color magnitude and color diagrams as you can, incorporate the distances when you can. And basically, please, please, please look at the images too. I cannot emphasize enough how important it is to look at the images. Some younger astronomers only like to work with the catalogs and they never look at the images. And this is rarely a very smart move. I have found published papers. There's one that claims a new discovery of a class of bright WISE sources, but they're not special sources. They're just saturated. And seriously, less than 3 minutes worth of work would have told those authors, or for that matter, the referee, that this was a completely garbage paper, but it's in the literature. You can, there's other slides even earlier in this talk series where you can see the source in WISE 3 and WISE 4 in the catalog, but you can't see it in the images. I mean, you've got to look at the images. We've got a ton of data available. There's so much archival data out there, but not every source has every band. And so some astronomers like to make statistical cuts and don't like giving each star individual attention. And so they make a cut at the very beginning saying that we're only going to care about sources that have detections in all bands. But for NITAR teams, we have a ton of people working on these projects. So let's put all that effort in. Let's pay attention to each and every source. Let's put in that time. Let's use everything we have. Let's spend that time. Let's make decisions using all the data we have. So for my NITAR teams, we usually do look at sources and images. We make SEDs. We make color magnitude diagrams, color diagrams. And if we have time, we can incorporate variability as well. So this means that you're going to have to try to play with the catalogs. You're going to come up with some color, and color magnitude plots to try. You're going to have to worry about AB versus Vega magnitudes. You're going to have to worry about limits versus detections. I don't think most teams have to worry about your own photometry, although you might. You are going to make SEDs. You will, before you're done, consider each source individually. And it is up to you guys if you want to make light curves or not. But then you can do time-dependent CMDs. And what I mean by that is this. So here's one particular object. On the left, you've got a spectral energy distribution. Here you can see the longest wavelength that we have for this one is 4.5 microns. So it has a little bit of a disk. This is its brightness in G band in the optical and an R band in the optical. And this is over years, right? Because those are days, so more than 1,000 days. So this is variability over years. But I can make a color magnitude diagram So this is ZTFG minus R. So this is the difference between those two bands here. And the color of those spots corresponds to the color in this diagram. So this is G versus G minus Z, because G is bluer than Z. So G minus Z versus G. And the red points are from late in the cycle, and the purple points are from early. So I've got a animated GIF here that's spelling out how the star is moving around in this diagram as a function of time. So early in the time series, it's moving around up here, and then it gets fainter and redder, and then it comes back up. See? Fainter and redder down here, and then it comes back up here. So time-dependent color magnitude diagrams, if your brain wasn't bent enough by now. Now, let's talk a little bit more about linking the SEDs and the color magnitude diagrams and color diagrams with some actual examples. I have some concrete examples that I want to show you here. So I just have a couple examples for several objects. The SED has different colors and points depending on the origin of the data, and I'll explain that later. But for all of these, the dashed line is where the photosphere would be, assuming that K band is on the photosphere, which is not always a good assumption. In the color magnitude diagrams and color diagrams, the little tiny black dots are everything in the catalog. The blue dots are everything that's interesting in the catalog, in other words, YSO candidates from any place. The green lines are where the main sequence should be. The dashed lines are models from any of a variety of places. The black arrows are generic reddening vectors. And the red star is the location of that specific star on that specific plot. If I can get a guess at the specific reddening, then I can guess at the reddening correction, in which case I can show you how the red star would move, and that's the gold dotted ghost point, but it's a guess. So let me show you what that means. Here is the spectral energy distribution. It's there. This is where the photosphere would be, assuming K is on the photosphere, which might not be a good assumption. J minus H versus H minus K. The little black dots are everything in the catalog. The blue dots are the short list of YSOs in this region of IC 417. The green line you can barely see is the main sequence. The dashed dot line is the reddened main sequence. There's the reddening vector. That dashed line is a model of where the big T-Tauri stars, the big disks, should be. That red star is where this object falls, given the JH and K that you see here. So you can see that it's got some reddening and some excess. This is IRAC1 versus IRAC1 minus 2. And again, black dots, everything in the catalog. Blue dots are the YSO candidates. There's the reddening vector. This is where the main sequence should be at 0 color. That red star is this object. You can see from the SED it's got a big excess. And indeed, you can see from this plot it's got a big excess. So this SED has a big excess, and the excess, the size of the excess, is dependent on wavelength. So technically, when you quote an IR excess size, you need to specify a wavelength. But can you do that math in your head in this plot? I can't. Can you do this math in your head? Yeah. 0.7 magnitudes. 0.7 magnitudes of excess at IRAC2. Boom. Done. That's part of why making this plot is useful. There's implicit assumptions in there, but still, the math is much easier here than it is there. I think you probably agree. Yes? Okay. Here's another star from IC 417. Another huge whopping excess. Is this the same guy? Star 2? Yeah, it is the same guy. Okay. Same guy. All right. Star 5. Here's a different SED. You can see it's got an inner disk hole with an excess out there. Here's IRAC1 versus IRAC2. Got a little bit of an excess here. Here's Gaia G versus B minus R. So an optical color magnitude diagram. Here, that is an isochrone at the distance of IC 417 for the 0 main sequence. And this one is an isochrone for about a 1,000,000-year-old star. And this star is the location of this object. And it is exactly the right place in the color magnitude diagram at exactly the right age to be a member of IC 417. So it's in exactly the right place. Yay! This one, look at this SED. Not much of an excess. Even just in the SED, you can tell that right away. And stop and think for a little while. Go back and look in the videos if you want to go back and look and see in the SED simulation videos that I had of stars without dust. Without You pause this video here, go back and look and see if you can figure out what this looks like. See if you can figure out if you think this is an early type star or not. Okay, I1 versus I1 minus I2. Bang on 0, no excess. G versus B minus R. Look how bright it is. It is an early type star. That's exactly what that SED looks like. That's what it's telling me. It's an early type star. It turns out to be a B star from the literature. This one doesn't have nearly as many points. Doesn't have an IR excess in the SED. No excess in this diagram. But this one I have pan stars data for. So pan G minus R versus I minus Z. So the stars that are down here are the ones that should have a G-band excess. Here the dashed lines are the models for main sequence. These guys down here, you can see that ghost star. It's the reddening uncertainty. If it's here, this is where it was observed. If the reddening I've guessed at is right, it should be here. But it's in the right place to be a G-band excess in this diagram. This one, there's a lot of scatter in the optical. So that could be from variability. Has a little bit of an excess here. May not be a significant excess given the size of the error bars on this point, it turns out. Here we've got R minus H alpha versus R minus I. Again, the black points are everything in the catalog, blue points are the things, the YSOs, green is the main sequence. And here's where this thing is. It is so bright at H alpha. No amount of reddening correction is going to take that H alpha away. So this thing is screamingly bright at H alpha. Something interesting is happening in this star. This one, very, very sparse SED in the optical. Look how fast that falls off. Go back and look at the reddening videos I had of the simulated SEDs. This object has very, very high reddening of AV of at least 10 magnitude, so there's no optical counterparts at all available. You can see where it falls in that J minus H versus H minus K diagram. It's all the way up here, so it has to be pushed all the way back to here. That's a lot of reddening. I1 versus I1 minus I2. Big excess. Okay, so what do you think about this one? Does it look like a young star? This is where this star falls in a whole bunch of diagrams that this team decided were the diagrams that they wanted to make. You may decide on different diagrams, but these are the diagrams that this team decided. J minus H versus H minus K, it's here. I1 versus I1 minus I2, it's here. Y1 minus Y2 versus Y3 minus Y4 is here. Pan Z versus R minus I, it's here. And with the reddening correction, it could be back here. G minus R versus I minus Z, it's here. And reddening corrections could put it here. R minus H alpha versus R minus I, it's here. G versus B minus R is here. When you correct for distance, because we do have a distance for this, G versus B minus R is here. Turns out that the distance, so when we were working on this project, we had two different data releases. So this is the Baylor-Jones adapted DR2 distance. Never mind about the details of that, but it's here with those error bars, and the distance of this object should be between, the cluster should be between those two solid lines. This is the actual parallax, which is what is measured. This is the DR3 release. And so it's still in the right distance. And in terms of location on the sky, it's here, which is not off the edges, it's closer into where we're expecting young stars to be. What do you think about this object? Is it a young star? Think about it and get back to me.